Ok, vamos a comenzar. Buenos días a este seminario institucional extraordinario que va a ser presentado por el doctor Philippe Bernal. Y el día de hoy van a tener la presentación que se llama From Architectonics to Geodynamics and Geohydrology, no, and Hydrogeology, Why Should We Go Back to the Caves? Y antes de comenzar voy a leer una breve semblanza del doctor. Philippe Bernard is an associate professor of the University of Montpellier, France. He is the director of the French National Academic GNNA's network. His first studies led him on the tracks of architectonics and Middle East and Mediterranean region using GPS and numerical modeling. Moving from plate boundaries to interplate deformations set him on the path where strain rates are on the order of few tens of millimeters per year. To quantify the plyo-quaternary uplift rates in France and study how architectonics can be induced by surface processes, he undertook the terrestrial cosmogenic nucleus path and went down in the caves to collect quartz pebbles. That's where he encouraged ghost rocks, cartogenesis, and hydrogeology. His current skills encompass active tectonics, GPS processing, geomorphology, geodynamics, karstology, and hydrogeology. So, thanks for coming, and the stage is yours.
Thank you. Well, and apologize for all the skills you had to list because it's 25 years of career and Pierre asked me to do something very special and difficult because he told me to kind of well show what I've done over the 25 years and I've done many things and I don't know exactly where I stand now. So I will try to go over that quite quickly, not to be too boring. And also just to say that I've been in Mexico well, it's first time I come to Mexico. So thanks for inviting me to giving this talk. And we've spent with my amazing partner something like more than 3 weeks in Mexico. So I'm trying to, I will try to link what I've done over the last 25 years with what I've seen over some part of Mexico. I haven't seen all Mexico, but I have seen some part. I went from the subduction zone to the Sierra Gorda, and so that's something I will try to discuss at the end. So first of all, Pierre asked me to present myself. So I've done many things. I've started to, oh, sorry, I have to stay there. I started to work on GPS, GNSS. We said GNSS no, but it's GPS. And then I moved to cave and I worked on active faults and different things. So that's something I will try to present today. That's my main work from the beginning, was to go in the field, set up some GPS station, then survey the position, then go back a few years later and do the new measurements. So I've worked in many places. All the places where you see black arrows are the place where I worked. So I worked in Himalaya, in Bhutan, for example, but I mostly work in this area in Iran and Turkey and Greece, and later on Morocco, and later on France. So we'll discuss all of that quite quickly today. And this also took me to geomorphology and hydrology in caves and even in the water. That's something I don't really like. I'm like a cat. I rather stay out of the water, but sometimes you have to go in the water. So if we start on the present-day kinematics of the Alpine Himalayan belt based on GNSS and modeling, so which has been a lot of, which has taken me a lot of time, and I worked at MIT for a while with colleagues like Rob Ranger and Simon McCluskey, and we work on the North Anatolian Fault and other faults. And doing so, if I try to summarize that, you probably know all of that, but the seismic cycle is, there's one part which is the interseismic part. It's the longest part of the seismic cycle. So that's when we don't have any earthquake, and that's usually what we measure with the GNSS. And then you have the earthquake. That's something you know quite well in Mexico. So there's this rupture on the fault. Then there is some post-seismic, which can last for a couple of years and sometimes longer than that. And then we start back on the interseismic, co-seismic, and so on. There's different idea on whether you always reach the same stress and then there's a stress drop due to the rupture or not. It depends, and that's something I'm not going to discuss today. That's something I want to show you is this. Oops. Uh, that's something quite impressive, and that's something I won't discuss. But maybe you've already seen that. It's the first time that an earthquake, a rupture, was taken on video. It was in Myanmar, and you see the fault and the motion associated to the fault and the fault propagating. So that's something quite interesting. And I must say that the first time I've been working on an earthquake for 25 years, and the first time I have experienced earthquake was a couple of weeks ago in Mexico, in Oaxaca. So I'm not really trying to experience this kind of rupture, and I'm more working and more focused on the anti-seismic deformation. So that's what we see here. There's no earthquake during these measurements, or we've corrected the earthquake. And if you look at the North Anatolian fault, so I don't know if you see my point, or maybe I use this pointer. So the North Anatolian fault, we are in Turkey. The North Anatolian fault is going all over this part, then in the Aegean and so on. And if you look at the velocity, we have a reference frame, so it's a Eurasia reference frame. There's no motion or almost no motion in the Black Sea. And then you see an increase of the velocities, a progressive increase in the velocities. And then you see all these velocities that clearly show that the Anatolian plate is moving toward the west in this Eurasian reference frame. So if we want to do geopolitics, that's something I usually do. And people more or less enjoy that, is that you probably don't know, but we have a big debate whether or not we should include Turkey in the European community. What we see is that based on geology and geodynamics, there's no discussion. Turkey is coming in the European community. So it's something I might at some point try to link the plate tectonics and geodynamic and geopolitics. That's probably something to do quite interesting, and I'm sure in Mexico too. So if we look at this part, so close from Istanbul, you see that these velocities are increasing toward the south. So that's what we see. You have the north here, south there, and we have something like 25 millimeter, 24 millimeter of strike slip motion on this North Anatolian fault. So based on that, we can do different modeling. I won't go into details, but what's interesting to see is that during the interseismic period, so no earthquake, no rupture, if you have one foot on each side of the fault, there's no motion of your feet. And this is like a rubber band that you're sharing, and you're sharing this rubber band until there is this threshold that is reached, and then you have the rupture. If we And that's something I've done. I've worked a lot on strike slip fault. So we were talking about the North Anatolian fault, but there's the East, the Dead Sea fault, there's the Tabriz fault in Iran, there's other faults there. And if you do synthesis of all these strike slip fault, and if you use a very simple model, so that's a cross section or a 3D view, you have the fault trace, no motion at the surface because we are during the interseismic deformation, so no rupture. And the only motion that we have is at depth in the lower crust where there is a free slip. And this free slip is what we see at the surface through this part of the elastic upper crust. So if we normalize all this deformation and we look at all this fault, there's clearly general trend, and we are different time period during the interseismic. And we don't see any change in this interseismic, so which was something kind of disappointing because we were expecting that based on the GNSS deformation, we could expect to say, oh, there's something going in the interseismic and maybe there will be an earthquake. So far, there's no clear evidence that during the interseismic, you can see that you are close from the end of the interseismic period, and maybe you will reach soon the coseismic, so you will reach a rupture. But that was part of the first things I've done for many years. And if we compare that, so that's for the geologist and that's for Pierre. Um, there is the GPS sleep rate, derived sleep rate. So based on this model, because we have to use a model to define a sleep rate of on the fault. And then on the other side, there are geomorphologists, paleoseismologists that estimate sleep rate on the fault based on the offset that they see in the field. And clearly, there's a good um, agreement between both. Sometimes the geodetic sleep rate are a little bit over the geological sleep rate, but it's not a problem because when you look at this model, what the GPS will give you is the boundary condition. So you have the plate motion, and sometimes the geologist they miss some of the deformation that it's not directly on the fault, but it's off fault. So clearly, no big issue. The big problem would be if this point was on this part, it would mean that the plates are not moving fast enough to explain the slip rate on the fault. So a quite good agreement, and that was something when I started to work. We had big argument with the geologists because they were saying that you cannot determine the slip rate on the fault based on few years of GPS measurements. It was just the beginning of the GPS, and there was this big argument. So I spent many years fighting with geologists to explain that GPS was good enough to estimate slip rate, and we could work together and do some nice things together. Um, I worked also on subduction zone. It's not the main part of my work, but this is, well, that's a good thing because you set up your GPS. It's in Crete. The sea is not as warm as the one in the Pacific when we went swimming in near Puerto Escondido. But it's nice you can swim while you do the measurement, so it's a good field work. And you can see notches there, so there's clearly evidence of uplift from time to time due to earthquakes. So it's interesting that you work on measuring the interseismic deformation, and you have the coseismic that's just beneath your measurements. When you do that, it's the Hellenic subduction and it's there, and the sites we were looking at is just right there at the tip of Crete. And when you do that, if you have a good geometry of the subduction interface, that's what we had for the Hellenic subduction with a kind of spatial subduction because it's a very flat one, and then it goes beneath the Crete, sorry, and then there's this thrust fault that's coming up at the surface just south of Crete. So if you do that, it's the same as the strike slip fault. We can do a simple elastic model. So I know that it's recorded, so I won't say that the Earth is just flat and elastic, but that's the model we use, flat Earth and elastic rheology. And for the previous model on the strike slip fault, I've told you that the fault was fully locked, so there's no motion on the fault. For subduction, we see, and even for strike slip fault, now we start to see that. Sometimes there's a little creep on the fault, but there's still some accumulation of stress, and then you will release an earthquake. So that's what happening in Crete. You have 40 millimeter of shortening, almost 40 millimeter of shortening on the subduction zone. But when you look at the GPS measurements that you have there and you do modeling and you take into account the coupling, so it's the ratio between the shortening that you have and the part that is the stress that is built up on the plate interface and that will release in an earthquake. Clearly what we see is that this is the Kefalonia fault. So the Kefalonia fault is there. It's fully locked, and that's the WRMS. So the lower value is the best value. So there's no way to say if the Kefalonia fault is fully locked or not. But when we look at the subduction interface, clearly you see that the WRMS value are the lowest for a very low coupling. So it means that you have 40 millimeter per year of shortening on the on the subduction zone, but you have only 10 to 20% of this 40 millimeter per year that will be released in an earthquake. So it's good point because it means that magnitude 8 earthquake that occur in beneath Crete from time to time, and that will the last one was more than 2,000 years ago, almost destroy a civilization in Crete. The recurrence time is on the order of 5 to 6,000 years, and it would be on the order of 500 to 1,000 years if the coupling was full at this part. So that's something that's quite interesting to look at also when you work on subduction zone, but you probably know that better than I do because you have this issue in Mexico. And then all of this is geodynamics. It's internal versus external processes. So what I've discussed so far was internal processes, so something that's related to either shortening or thickening related to the plate motion, but also sometimes atmospheric upwelling or slab detachment. But then there are also other processes like ice building, when you put ice sheet on the earth, or erosional unloading. And what I'm going to try to show you that is sometimes erosion can lead to shortening and thickening, and we don't need to refer to internal forces to explain shortening or extension in the mountain ranges. So that's where I came when I went back to France after working at MIT, is that so I've been working on places like you see the scale, 10 millimeter per year. So it's 25 millimeter per year. It's sometimes like 40 millimeter per year. Then I worked in Morocco, was 4 millimeter per year. So slowly I went in places where you don't see the vector anymore. It's on the order of 0.1 millimeter per year or less. And we have many GPS stations, but now you see the scale, it's 0.2 millimeter per year, 0.5 millimeter per year. So when you start to work in France with GPS, you're kind of either you start to drink a lot of tequila to forget that uh, there's nothing to do and you're just calibrating antenna, or you dig a little bit more in the data. And something that was interesting when we started to work and get data, and we had a long time of recording data in France, so we started to see that even for the horizontal motion, we couldn't see much. There was a signal on the vertical motion. We are looking at vertical motion in this part of the slide, and we are going up to 2 millimeter per year in the Alps. So that was something quite interesting because so far we've been working with GPS with large horizontal motion, not so much in vertical or a little bit. And then we're moving into anthroplate deformation in Western Europe, was the other way around. Not very large horizontal motion, but kind of large vertical motion. So that's when you have to start to work and more on the data, but there's still well, there is seismicity. I forgot to put the seismic the map of the earthquakes, but we have many earthquake, not so strong, but many earthquake in the Alps, in the Pyrenees. We have also earthquake in these places, and then some around there. So if you work on the data and try to filter this data, you can come up with this velocity field. Still, you see the value, it's very, well, there's an issue in this. But the velocity are very, very small. But when you do that, you derive strain rate. So you have a strain rate field there, very low. One here, it's a 1 nanostrain, so it's something that is very low. It's on the order of, it's just like you're looking at 1 millimeter of shortening or extension over a length of 1,000 kilometers. So we are just at the limit of what we can see with GPS. And yet, when you do that and when you have earthquakes, the earthquake arrived after we produced this strain rate. So we didn't cheat. it's okay. Uh, there was this earthquake in France, the first one with surface rupture from well, that was well documented in this on the fault that we call the seventh fault, almost 5 in magnitude, something very small, but it was the depth of the rupture was 1 kilometer, so that's why it went up to the surface. And the focal mechanism clearly was in agreement with what we have produced with the GPS. So once again, we can use GPS to look at this deformation, even they are very slow. It's the same for the Alps. We're looking in the Alps here. We have strain rate on the order of 2 nanostrain. And the difference in the Alps is that in the central part of the Alps, we have a normal fault and extension. So that's something we had to explain. People argue that it was related to deep processes, mainly slab break off, because there is still a slab beneath the Alps, or mantle flow, and they ruled the upper process to something that was very not important to the deformation that we see in the Alps. So I'm just going to try to show you that, in fact, it's probably the other way around. When you load the crust with ice, what's happening is that since you're loading the plate, you have shortening just beneath the ice cap, and you will have extension at depths, but this won't appear in the seismicity because this is part of the lower crust. In the upper crust, what you should see is stress beneath the ice sheet. And then when this ice sheet will start to melt, the plate will come back to the original state. So, in fact, what's interesting is that there is quite something not so easy to pick up with GPS, because when you do that, when you load the plate, it means that you have shortening. So if you have GPS, they will show you that it's compression, and that's what you see in the seismicity, you have compression. But then when you start to unload the plate, if you have GPS on both sides of this, the GPS will start to move apart. So the GPS signal will show you that it's well, you will expect extension, so you will expect normal fault. Whether in fact you are still compressing your spring, and so in fact it's still thrust fault that you could see. So strain will give you extension, stress will show you compression. So it's something quite interesting, and that's what we see in the Alps, is that if you model what we know from the little ice age, from the global, from the maximum ice that we had in the Alps, so 10,000 years ago, and you try to fit that to the focal mechanism that we have in the Alps, that's the model, that's the uncertainties that we have on the model, and that's the observation. So clearly, we are not explaining the kinematics of the fault based on the focal mechanism with the GPS and with the modeling. So it means that we have to find something else to explain this deformation, and this is not related to the GR. So that's something that we have in common with the previous author, that is clearly not the glacial isostatic adjustment that is doing the seismicity in the Alps. But then, if you look at the focal mechanism, so we are looking at the Alps, focal mechanism will show you that the stress state of the crust beneath the highest part of the Alps is extension, and then you have compression in the foothills of the range. So it's not working because we don't have compression. We have to find something else to explain that. And then that's when we start to play with the erosion. If you put erosion on the mountain range and we don't have boundary conditions are very low. We don't really know if it's compression or extension. So if you have enough erosion on this mountain range, what you will see is uplift, mostly uplift, but you see that the velocity here, they are uh, going apart from each other. So what you expect as focal mechanism in the central part of the mountain range is extension. And what you expect in this foothill part of the mountain is compression. And it's clearly what the seismologist told us, is that based on focal mechanism, you have compression there and extension in this part. So, but then if you want to do that correctly for the Alps, you have to get the erosion rate over the mountain range, over the Alps, and over the Massif Central. We'll see later on. So that's part of where you go in the water and you collect quartz pebble, because if you collect quartz pebble and you use cosmogenic nucleids, then you will be able to estimate erosion rate. So I won't go into detail. If people want to discuss that, we can discuss that later on. But the concentration that you will measure in the quartz pebble there will be related to the erosion rate that you have upslope in the watershed. In fact, the production of this cosmogenic nucleid is just between 30-meter depths and the surface. So the slower the sample takes to go from minus 30 meters to the surface and then in the river, the highest concentration you will have. If it's crossed very quickly this window, this 30-meter windows, then the concentration will be very low. So based on this concentration, we can estimate erosion rate of the watershed. And if you take this quartz pebble, you put it in a cave at more than 30-meter depths, then you have new uh, part of the equation there. That's the burial age. So you can estimate the time since this pebble was buried in the cave. So we can do two things with one. Well, then we have to use the beryllium and aluminum to do that. For the erosion, we can just use the beryllium. So just to sum it up, if you collect quartz pebble in the river, that tell you what is the erosion upslope in the watershed. And if you collect quartz pebble in cave, that will tell you when the river was flowing in the cave. So if you use this, many people have worked in the Alps to estimate erosion rate. So you have a map of erosion rate over the Alps. So sometimes it goes up to 1 kilometer per million year of erosion. So it's quite something. And if you use that in a model where you use isostatic and flexure, it's what you will get for the Alps. This is what we will get for the Alps. So this is the erosion-induced tilting rate. We have geomorphologists reporting tilting rate in this area or in this area. And you have the model, you have the observed value. They are quite consistent. And you can also look at the uplift rate because the same geologists and geomorphologists report uplift rate based on river incision, for example, in this part. And you have, so it's related also to the tilt, but you have 100 meter per million year of incision in this area. And the uplift that we see in the model is on the order of 200 meters per million year. Here it's 300 and so on. So it's quite working well. And it means that if we use only erosion, we could explain almost all the geomorphology of the mountain range that we have there. So it's quite interesting, and it means that in anthroplate deformation, you really have to take into account erosion rates because this can explain a lot of the geomorphology that you see right now. And so I will move in the Massif Central. So we are looking at the Alps, and we will move south of the Massif Central in the Grand Coast area. Grand Coasts are quite like the Sierra Gorda, where we were a few days ago. It's mostly limestone, you have big canyons and you have many caves in this limestone plateaus. And the good point is that we have also granite and schist upslope of this river, so we can carry quartz pebbles in the river, and so we can estimate erosion rate, but we can also estimate a burial dating in caves. If we look profile along a profile here, so Massif Central is right there, the Grand Coast are in this part, and so if we do a profile where you see that we have also the Mediterranean Sea and we have sedimentation there because the Rhone Valley is going in this place and putting a lot of sediment in this area. We can also do a simple elastic model. So that's the topography, Massif Central. You have the Gold Coast in this part, and then you have the plateau and then the Mediterranean Sea. We know that there is a sedimentation rate on the order of 200 meters per million years in this area, and we have, based on this estimation of erosion rate, something like up to 100 meters per million year of erosion in the Massif Central. So if we put that in the model and use the isostatic answer response to this erosion and sedimentation, this is the uplift or the subsidence that we will get. So we have an uplift rate on the order of 100 meters per million year. Then we have bend in there, and then we have subsidence in the Mediterranean Sea. If we look at the strain induced, it means that this is normal faulting. We should see normal faulting in this part if at some point we have a quake, and we should see stress fault in this part in the Mediterranean Sea if earthquake occurs also. So far, we don't have any earthquake and focal mechanism to discuss that, so I can say a lot of things, and I don't have any constraint on that. So if we use the quartz in the cave, we can see if the model is okay or not, and if we have this uplift rates. So that's part. So that's a picture of part of the Grand Course. You have a big canyon here. It's the Vis. So it's a 350-meter deep canyon. You have the granite of the seven north of this plateau, and they are flowing. So the quartz are flowing in this part, and then it can be buried in the cave. So the game is to look for caves that are different levels. Based on what the hydrologist told us when we started that, is that you expect to have the water going in the plateau and then having forming by dissolution a level that's related to the cave. So that's where you put the quartz pebble, and that's where we are going to collect them, because in the second time, when there is another incision phase, you have this abundant alluvium that you can collect, and if you estimate the age of this alluvium and you have the difference of altitude, then you have an incision rate, and if the river is kind of flat, then you can convert that to uplift rates. So that's what we've done in many caves and the Grand Course. When you look at that, it's not so easy to see a trend. You have the elevation relative to the closest river, and you have the burial age. So if I remove some of the point, the gray, all the gray one that you have there, so let's just remove them, then you start to see a trend. You have a trend, you have two trends, in fact. You have one trend for the caves that are north of the sevenfold zone, and you have one trend for the caves that are south of the sevenfold zone. This gives you on the order of 90 meters per million year of incision for the canyons that we see there, and this gives you on the order of 40 meters per million year of incision for the canyon that we have here, the Arrow River. So if we look at the model will tell you that you have something like 100 meters per million years, so it's quite consistent with what we have here. And if we are close from the fault, because the river here is close from the fault, we are on the order of 20-30 meter per million year, which is not so bad compared to what we have based on geomorphology. Uh, so what we didn't expect, I will come back to these gray samples. These are the samples that we collected not on the side of the canyon, but in the plateau. And when you look at these samples, they are too young compared to what we know of the incision, right? So it means that these quartz pebbles were put in the cave when the river was already uh, lower in elevation. So that's lead us to propose something that has already been proposed by previous author in Belgium, for example. But we have some pre-structuration that is related to alteration. So for some of you that know the granite will be when it's altered, you have arenite, kind of sands of granite, and it's the same. And at some point, if you cut part of the limestone that is that has been altered, you can remove this altered rock, what we call ghost rocks, because you still have the layering of the limestone, but you can put the finger in, and it's not cohesive. And you remove that, and you will form the cave instead of having the water dissolving the limestone from the upper part of the plateau toward the lower part of the plateau. It's going the other way around. You're removing the altered rocks and progressively moving upward and opening voids that will be filled up with the alluvium that you have on the surface. So that's why we had this very strange results. So now back to Mexico. That's part of the when you travel from Conca to the Sótano del Barro. There's a nice piste, and if you look at that, these are limestones, and if you look at what you see in the geomorphology here, it's exactly what we see in the Grand Coast. These are corridors of altered rocks, and these are places where you will have higher porosity, where you will put more water, and it's usually where you will stock the water, and that's what explains that you have still spring during dry season. And that can explain also the Sótano del Barro. I guess you know this cave. It's the second largest cave, sinkhole in the world. It's 400 meters by 200 meters, so it's quite impressive to see that from the road. And to explain this largest void, it's hard to explain it by water flowing into it. You have to have a first phase of alteration. Then when you will start to remove the altered rock, you will have a collapse of big blocks, and you will start to form large chambers like this one. And that's the Sótano del Barro that you can see from above. And I will so just to say that the purpose of the travel was holidays, but was also work. And the Sierra Gorda we've discovered with Katia a landscape that is in some way similar to the Grand Coast, especially because there's limestone, it's karstic area. And the question that I have no after spending a week in the Sierra Gorda is could karstology and numerical modeling of the erosion induce, because clearly when you see the slope that you have, there's still some active process of erosion, incision. There are deep canyons, or well, you know that better than I do. And so could this bring new insight on the understanding of the seismicity of the area, and especially from, well, I know it could, if you do erosion on this mountain, you could probably have normal faulting rather than shortening. So it's quite interesting because the subduction is not so far. So you have this transition between plate boundary to intraplate deformation. And since Katia has a PhD in anthropology and she's pushing me toward this part, we've discussed with different people about that. And the question is how the inhabitants of the Sierra relate to the underground world. So this cave, like the Sotano, but also uh, the seismicity, since we have since probably seismicity, well, based on discussion with we had with Pierre, is the seismicity, the recurrence time is a longer recurrence time than what we have for subduction zone. So could the oral literature, the myth and legends, maybe you know the work of Vitaliano that proposed the geomythology based on oral literature, you can bring information. So could this bring additional information on the geological setting, but also on the seismicity, the not historical seismicity, but all the deformation is affecting the Sierra, and so that's probably something that we uh, been discussing with Pierre when he was in France. We have a nice discussion at the lab, and now we will probably work on that, especially also since working on that, maybe we can revert that, and you could use also this to discuss with the population and then have a population that is more prepared in case of earthquake. So, or you can use that also as a preparation for the population to earthquake is something interesting. And I hope I haven't been too long. Okay. So that's the end. Well, sorry I couldn't do it in Spanish. I haven't took Spanish classes at college. I'll try to improve my Spanish in the next few years. Maybe next time I will be able to do something in Spanish. Well, muchas gracias.
Very much. Very interesting presentation. So,
Thanks for your talk, but I have a couple of questions. The first is the erosion process is quite slow. So, and the possibility of earthquakes that occur, I see the Alps, it seems is fairly small magnitude events. So I would think that this process is slow enough that it doesn't necessarily increment or increase the deformation to the extent of triggering large events. I suspect that's the case. Is that something you considered?
Well, it's something we've been working on. If you look at seismicity in anthroplate domain, sometimes you have large earthquake. Usually the seismicity is really in the upper part of the crust. So the question is how long we've been looking at how long you could build up this trace. And based on what we know on the rheology, in fact, you can erosion as soon as you put topography. Erosion is working on the topography. So when you remove the boundary condition because there's no more boundary plate, you increase the stress, and even for over 2 million years, depending on the geotherm of the plate, you can still build up stress. So in 2 million years, even if you have a slow erosion on the order of 50 meter per million year, you can build up stresses that are enough to do, well, large earthquake, I don't know, but maybe magnitude 6, maybe more, maybe magnitude 7. We don't know. Question, I don't know, maybe you know the New Madrid earthquake in the United States.
Yeah.
There was a proposition of that this was related also to erosion. It's not exactly the same, but it's more or less the same idea that in the anthroplate deformation you can build up stresses, and then you can reach magnitude.
Over time, you will generate
Yeah.
sufficient.
So the recurrence time could be long, maybe, but you can, if you are with a cold geotherm, you could maybe build these traits for 2 million years or more, and over that time. So it means that you won't do an earthquake every 2 million years, but you can have an earthquake in the places, and then maybe no more earthquake in that places, and maybe you will have another earthquake and another fault. So the question is that do we really have this seismic cycle on these faults when we are in anthroplate deformation, or is it one earthquake and then nothing happening on this fault, and maybe one earthquake on another fault. So it's cracking from places to places and not something that is going on always on the same fault. But the erosion is enough to even if in a low erosion context, this is enough to maybe explain earthquakes.
The other thing I thought was interesting was you work on the Anatolian Fault,
Yes.
and you didn't see necessarily any observations over the interseismic cycle, over the interseismic
Yep.
period. And I'm wondering if, I mean, those are all surface measurements.
Yes.
So is there a possibility that, because I assume that Anatolian Fault has a seismogenic width similar to the San Andreas,
Yes.
15
Yeah.
kilometers or so.
Yeah.
So is it possible that there might be something that could be observable at depth rather than surface?
Yes. So we start to see, especially with INSAR, we start to see that sometimes the fault is slipping a bit, like the San Andreas fault. If you go in the San Francisco area, you have some creep at the surface, but still with this creep, you will produce a large earthquake. So at depths, I don't know exactly. There was something interesting with the large, big earthquake on the East Anatolian fault. Looking at the coseismic related to that, the wall plate moved more than what we expect with the classical model. When you look at the classical coseismic rupture, with the East Anatolian fault, you don't expect to have motion near Istanbul, near the Marmara region, and in fact there was this displacement. So clearly that we see that the wall plate is in extension, and if you open the zip in the East Anatolian fault, the wall plate is moving toward the west and moving more than what we expect. So at depths, I don't know exactly what's going on. We have planned to maybe set up tilt meters and strain meters in close from the North Anatolian fault, because this could, when you work on a strike slip fault that's vertical, it's hard to see what's going on compared to a subduction zone when you're on top of the subduction zone. So if we put strain meters and tilt meters, maybe we will have information on what's going on at depths, and to see if there are some slip that maybe is more at depth or not. So, but I don't have information on that yet with what we have as observation right now.
So thank you very much. I found it very, very interesting that you're starting to use caves to get a geodynamic view of what's happening. As far as I understand, you are interpreting the different levels of the cave to represent the uplift in the mountain of the body. That would suggest that it is that the uplift is not gradual, but actually a very discrete, that it is going from one level to the other very rapidly.
Well, that's something that's quite, we have big debates with hydrologists and people working in the karst, because I haven't found the one geomorphologist who say that terraces were related to cave levels. And being more on the geophysicist side, I don't see why you have canyons there and you don't have canyons there. You expect the law of physics to be the same, even if it's dark in the cave. And so what you would expect, if the river is flowing there and if there is this uplift, then you should have a canyon that is carving progressively in a depth in the ground. So that's why we went there. We went looking for alluvium with this idea, because the hydrologist told us, well, this is related. So if you find this, it's related to a period of stability of the river, and then but to me, it's not it. And so we especially pick up caves in this plateau, sometimes few kilometers from the canyon, that are different levels. And we went in these levels, collected pebbles, and this clearly was not related to what was going on the canyon. So that's why we came up with this model, but once again, we are not the first one to propose that, is that this is related to a previous phase. It could even be related to the diagenesis of the sediments, where you have escape of fluids. You will have special part of the carbonates that can be dissolved. And so during the time that these carbonates are below the water level, you have a very low circulation of water. You have dissolution. So we're working now with people that are working on bacteria to see if the bacteria could explain also the alteration of these rocks. And so you are preparing places where you have this kind of levels that are not related to the river. And in fact, these levels are just showing that during a time period when this limestone was beneath the water, the base level, you had circulation in this part, and there is no, to me, because for a lot of people it's not the case, there is no relation between the level and the velocities of the incision. It's just when this canyon will carve in this part, you will empty this part and you will put quartz pebble in there, but the level was not related to a phase of stability of the river. So I don't know if I'm very clear, but levels to me are not related to the incision of the river. They are related to a previous phase of structuration of the limestone and the alteration of the limestone. And this we should have canyons, underground canyons, and not levels in the cave. So I'm clearly not using the cave level as a marker of the incision or stability of the river at some point.
Because what's been done in the Great Canyon in the US is to actually date carbonates
Yes.
that are indicating when the cave was above the water level.
Yep.
Maybe a good idea to do a comparison between getting from cosmogenic nuclides.
Yeah, so we haven't done a lot of, because we don't have because I don't have collaboration with people working on dating of spelotherms, and because also this is also we have to work on it's not uranium thorium, it's uranium lead, yeah. And so, and usually when I bring pieces of the spelotherms that I have, the geochemist will say, well, your calcite is really shitty and we cannot work on that. So, but in places it's something very interesting, and clearly it's dating, and in the Sierra Gorda it could be something interesting, because I don't know if you don't I don't know the geology, so I don't know if there are so many quartz pebbles in the cave in the Sierra Gorda, but working on the edge of the spelotherms and trying to see if we have this progressive abandonment of the water flowing in the cave could be something very interesting, yes. And I haven't been in cave in the United States, but looking at the report of the largest cave like Mammoth Cave and other in the Grand Canyon, uh, when you look at the report, there's clearly they don't explain this like that. They don't explain this with ghost rocks, but there's clearly some evidence of ghost rocks, because you can see that they explain that sometimes the rocks you still see the layering, but the rocks, they will be powdery and they will go away if you start to scratch this. And it's clearly, so it's you can see it also as hypogenesis, carstogenesis, with the hypogene phases will produce ghost rocks. So this part is hypogene, and then you start to work to, and then you start to move to epigenic processes that will remove the hypogene part, remove the ghost rocks, and then so it's a continuum. In fact, it's not two different things.
We will talk about later on about the date.
Yeah, sure.
just a couple more curious questions about other things, but I work with sea level dynamics, and sedimentary isostatic and tectonics play a role to know how the coast will react in the future when we have this estimation of a sea level rise. So I work mostly in the Atlantic side because we have this sort of passive margin, so it's big and easy for us to understand. But at some point, I would like to work also in the Pacific side. There are some works on Holocene sea level in the Chilean side of the coast, but I want to do it in Mexico. So the questions are, when you are working with GNSS surveys, how often do you need to back to field to start to measure this rate of slip or not? Like how easy or not are the correlations of what you are seeing with these actual GNSS surveys and when you are looking with what geological sites or the geology says about the past movements in the lab, and if you are working with Ertica GPS or with Canop, and what you can do when you are in a place when you have no signal there. So
A lot of questions. Well, GPS it depends on the rate. Often you have to go back to and know there is low cost GNSS receiver. So you can also set them up as a continuous recording, and then or you compare that to geology is based on the model, so you have to work on models. So that's why it's interesting. If well, I had something that if that's something very sketchy that I saw quickly this morning at breakfast while discussing with Pierre. It's a cross section, so you have the subduction interface there, and what you see if you look at the shit. Well, they are velocity in Mexico. Unfortunately, they disappeared from there. But this is related to the how you stress that, and so that's why I put this spring. The spring is related to the stress buildup, and at some point it will be a release on an earthquake. But then you have to correct from that signal to know where the transition is. So that's why there are question marks where the transition is between the plate boundary region there and the intraplate deformation there. So I put normal fault, but it's just maybe not. It's just based on what we've seen last week. I haven't seen normal fault. Just suspect that maybe there could be normal fault, and so this will be related to the model that you will do and how you couple the subduction. So there are clearly some information on where you put the transition between these two, and this a good way to understand that is compare the geomorphology and the geology that you will see there. If we see normal faults, if this is something that is happening, I don't know, so don't take it as granted. Maybe it's a reverse fault. But if we see that, then we could maybe say, okay, the transition is somewhere in this part, and it could also help you to constrain your elastic deformation of the GPS. And then, or you can relate that to uplift rate to the coseismic. So it's clearly how often you go back there. It's since the rates are quite fast, you can go back there quite often. It's better because also on the subduction you can have slow slip event and stuff like that. So it's better to have continuous deformation anyway, continuous recording anyway. But then it's how you will model this whole part and taking also into account the erosion. So it clearly is quite something interesting. And the last question was RTK. If you don't have because if you have a good 4G connection, that's clearly easy to relate to one base, not too far. But otherwise, you have to put one base in a place, and you have your rover. But the good thing is to record the base and then to compute the base position related to one of the continuous stations that you have somewhere else. Because in case of earthquake, you can come back and you can see the differences related to the earthquake.
Thank you. Okay, thank you again for the time.
Okay. Oh, that's the